Hello and welcome back to our discussion of Chapter 13, dealing which we're addressing here in week 6. So jumping straight into Chapter 13, we're talking about probabilistic reasoning. So starting with uh, the first bit here of representing knowledge in an uncertain domain. So sometimes we have situations where we don't necessarily know with certainty what's going on. So a classic example, and one that's discussed in your text, deals with this concept of an alarm's going off. So there's several things that could have caused the alarm to go off, and more importantly, two people call you telling you that your alarm is going off, right? So given all of those factors, so the alarm could be going off because there's a burglar, it could be going off because there's an earthquake, and it may be going, maybe it's not your alarm that's going off, maybe it's somebody else's, and John and Mary are confused, or John or Mary is confused. So the basic idea here is that we have tables that describe essentially probabilities associated with these various items, and because of the type of network it is, it allows us to do some interesting calculations. I'm not going to go through this in great detail, but understand that the whole point of it is to capture and represent information in a situation where it's not certain exactly what's going on, and that's where we're dealing with this probabilistic approach. Moving on to semantics of Bayesian nets and networks. So we're kind of seeing a little bit of one there in the example of the alarm. It's basically a directed acyclic graph, one node per random variable. Those are very specific ways of talking about it. So in that case, a particular random variable was a person. So Mary was a random variable, as with earthquake and robbery or burglary, whatever the choice was. A conditional probability table exists for each one of those nodes. And whenever you combine those together, you end up with basically a bit of calculating the conditional probabilities associated with the joint conditional probabilities associated with the various traversals. So pretty handy way of representing information. So continuing that concept, we can talk about exact inference inside of Bayesian networks, and this is where we're doing things in a very kind of direct sort of way. With given, granted, we're dealing with probabilistic stuff, but we're not doing some sort of sampling approach. We're basically calculating it directly. Inference is used to calculate some useful information from a joint probability distribution. So, very good definition to kind of keep in mind there. And we also have this concept of the most likely explanation. So the most likely explanation is something which is going to be kind of like the thing that is likely what had caused it, as the name would imply. We also have this concept of inference by enumeration, and it's essentially an iterative process where you go through and calculate all kinds of each of the values, summing them up, and then calculating at the end essentially some hidden values. There's given unlimited time, inference and is relatively easy, but it is going to be take quite a while to work through. Um, and a bit of a reminder there of inference by enumeration example. I'm not going to go through that. And kind of a visual representation of that same sort of inference by enumeration example as well. And if this is a topic that is of much interest to you, then feel free to dig into it and gain some additional knowledge. But it's, again, what we're doing here is essentially a survey. We're very briefly skimming across the tops of all these domains, and I'm trying to not drag you down into the details of each one. So one of the problems with inference by enumeration is that it is relatively slow, and part of that is, as the slide points out, is because the whole joint distributions are calculated before you start figuring out what the hidden variables are. And so there's a way that you can make it better by eliminating by something called variable elimination. But you're still ending up with something that's basically NP hard, and NP hard means it's going to take a while. That's the short version of that kind of definition. However, it's still going to be faster than a full-fledged inference by enumeration. Causal chains is the basic idea of explaining that something caused something that caused something, and representing that in a probabilistic way. So the example that you see there is that the probability of a low pressure environments associated with the probability of rain, which has something to do with traffic occurring because traffic is always worse than the rain. So you can kind of infer those things. Is it guaranteed in X independence of Z? Definitely not. And in fact, it has some sort of a relationship with it, although certainly probably not the only cause of traffic. Um, and so that's a decent example of how that might work out. Uh, and it's the same basic thing. So moving on to common cause, sometimes there are one thing might cause something else to occur. So this is the example of back when people actually went to labs in a school to do their work for an assignment. The lab would be full. Most likely there could be a project due. And also, if there is a place where people discuss their schoolwork, it might also be busy. So forums might also be very busy. And is there a guarantee of independence between X and Z? Again, no. Although there probably is some sort of a common sort of factor going on here, but they're definitely not independent. And I'll skip over that as well. And sometimes there's this concept of a common effect. So something that is a result of something else. In this case, the common effect is um, traffic. That's what the effect is, and the multiple things might cause it, including rain or potentially um, a ball game. So lots of people going to a ball game. And then moving on to common effect. uh, we look at the last configuration, two causes of one effect. So this is kind of that V structure we've been talking about all along. Are X and Y independent? Maybe, but so this is saying yes in the case that the ball game and the rain cause traffic, but they are not correlated. So you may want to think these things through. So the general case of conditional independence, um, and this is a way of figuring out, given a Bayesian network, that two variables independent. So how can you figure that out? And the answer is you can look at the graph and figure it out. So basically, there are three sort of ways that we can figure that out, and we'll drill into each one of them. Reachability. So the recipe is essentially shade evidence nodes looking for paths in the resulting graph. Uh, if two nodes are not connected by any undirected path, not blocked by a shaded node, they are conditionally independent. So basically, you can figure it out that given the direction that you can go, that some things might be independent or not. So almost works, but not quite. Where does it break? And the answer is the V structure at T doesn't count as a link in a path unless active. So basically, we're showing here that it's potentially helpful, but doesn't always get there. Active inactive paths are X and Y in conditionally independent given evidence variable Z in calculating through active versus inactive paths and looking for something that is it basically not blocked, right? So if you have a block, then it's going to mess up the active segment. And then this concept of deseparation, and basically check all undirected paths and between x sub I and x sub j. And if one or more is active, then independence is not guaranteed. Um, then otherwise, if all paths are inactive, then independence is guaranteed. So that's one basic way of figuring out if things are uh, the general case of being conditionally independent. And definitely there are some structural implications of the Bayesian net, as we just kind of talked about with figuring it out using various algorithms. And I'll skip over the topology distribution. So moving on to approximate inference in Bayesian networks. And the idea here is that you can't necessarily rely on a direct sort of way of calculating it, so we have to do something it's typically involving some form of sampling. So sampling is going to be involved because it's just too much, too computationally expensive, or too much space to calculate all of the actual values. So instead, we do some form um, of calculations. And again, revisiting that a Bayesian net is a directed acyclic graph, one node per random variable. And moving on to this concept of sampling. Um, so it's kind of like a repeated simulation. And for those of you who had the simulation course, you hopefully can see how that might be. Uh, and it's the basic idea is that you're going to draw in samples um, from a sampling distribution S and compute an approximate posterior probability, and then show this converges to a true probability. And the Y sample is that you can get samples from a distribution you don't know, versus if you have to know the true shape of the distribution. And getting a sampler is faster than computing the right answer because of the space and difficulty in those calculations. So drilling into the various types of sampling, moving into prior sampling. Um, oh, where did it go? Yeah. So the basic idea here is that there are several types of sampling that we'll use, and you're doing so in a way so that you can select values that might get you where you're wanting to go. So here we are, prior sampling. The slide was in the wrong spot. There are basically kind of four types of sampling that we're going to be doing inside of Bayesian nets. Prior sampling, rejection sampling, likelihood weighting, and Gibbs sampling. We're going to just briefly touch on these things, as we are most of the material in this course, because it's we could spend all semester talking about basically one of these topics. So prior sampling, the basic idea uh, is figuring it out, as the name somewhat would imply, um, by looking at parents and so on. So you're essentially doing it beforehand, and I'm trying not to restate the same words. Rejection sampling, you figure out those things that you don't really want based upon some criteria, um, and so you essentially can remove them sooner than later. And the more things that you prune whenever you're doing any kind of computation, the better. And sort of a simplistic algorithm for how to do this. If it's not consistent with the evidence, then reject it, essentially. And with any form of sampling, you have the potential of missing kind of the true answer of things. A likelihood weighting, again, another approach to dealing with the inability to calculate the full values based upon time and space constraints. So you may very well use some mechanism of determining what is likely the situation and adjusting your algorithm appropriately. And a brief kind of algorithm of that, and showing that the key concept here is you're throwing in a weight in addition to so the probability. So if there is some evidence, then you're going to put a higher weight on something, versus if there's not evidence, is the gist of it. And running through the last little few of these. And then the last type of sampling that we'll talk about in this chapter um, is Gibbs sampling. Um, it's this is a fairly complex topic, but the basic idea is to jump to the bit that matters, is you're using a form of Markov chain Monte Carlo sampling to calculate it. The reason you're doing this is that it's just kind of hard to do it some other way. If you want to learn more about it, that link there is definitely a place to go take a look. And it can give you a pretty good background on it if it's a topic that is of interest to you. The basic idea is, you can kind of see it visually here, but it is dealing with Markov chains, and so non-trivial topic. And with that, we wrapped up our discussion of chapter 13. As always, if you have any questions about any of this material, feel free to reach out to me. Keep in mind that we're trying to keep this at a very high level, I'm skipping over a lot of the details of these sort of statistically based classes, primarily so that we can stay focused on the concepts more so than the specifics and the details. Again, if you have any questions, let me know. That's what I'm here for. Stay safe, and we'll talk again next week.